Hello students, today we will study about the real numbers, that is the topic of standard 10 chapter number 1. So in this chapter we study the main two concepts. First one is Euclid's division lemma and second one is fundamental theorem of arithmetic. So in today's lecture we will study the first topic, that is Euclid's division lemma. You have already studied about the division algorithms for the numbers and for the polynomials also. So that same topic, that same concept of division algorithm, that we have to study as a Euclid's division lemma. Right? Let's suppose there are two numbers, one is 17 and one is 6. We want to divide this 17 with 6. Then what will happen? We divide 17 with 6. Then we get 6 2s are 12 and we get 5 as a remainder. So we can represent 17 as 6 multiplied by 2 plus 5. Right? 6 2s are 12 plus 5 is equals to 17. So according to the division algorithm, this 17 is our dividend, this 6 is divisor, 2 is the quotient and 5 is the remainder. So like this is a division, one type of division algorithm. Now second example, we want to divide this 5 with 12. We know that this division is not possible because the 5 is smaller, 12 is greater. So we can represent it as 5 is equals to 12 multiplied by 0 plus 5. Right? See the third example, 20 and 4. We want to divide 20 with 4. So we can write down 20 is equals to 4 multiplied by 5 plus 0. Now, if we want to say it, we can say that for the first example, 6 goes 2 times and give the remainder 5 for 17s. Right? Similarly, for the number 5, 12 goes 0 times and give the 5 as a remainder. In the same way, for third example, for 20 we can say that for 20, 4 goes 5 times and gives 0 as a remainder. Right? So here one thing that we have to notice that the value of remainder, this and this. So the remainder get any value from 0 to any positive integer. It may be 0, it may be 1, 2, 3, 4, 5, any positive integer and 0. In the same way, this number we get as a quotient is also have a value 0, 2, 0 and 5. So the quotient is also have a value from 0 to any positive integer. It may be 0, 1, 2, 3, 4 or any positive integer. So both quotient and remainder are have a value from 0 to any positive integer. So in general form, if we want to write down these things, we can write down it as A is equals to BQ plus R. A is equals to BQ plus R. For each case, our A is 12, 5 and 20, and for these three cases, our B is 6, 12 and 4. So what are A and B? A and B are also positive integers. Then what are the Q and R? Q and R are also positive integer and 0. Right? So this Euclid's division lemma that we have to study is only for the positive integers and 0. We are not using the negative integers in this Euclid's division lemma. Okay. So what is the statement of Euclid's division lemma? By studying these three examples, now we will study the statement. That is called as theorem 1.1, and the statement is given positive integers a and b, there exist unique integers p and q and r satisfying a is equals to bq plus r. So we have already seen that two positive integer a and b we have taken as 17, 6, 5, 12 and 20. There exist unique integers q and r. Why the use word unique? Let's take this example 17 and 6. For this example, this is a, this is b, this is q and this is r. So the q is 2 and r is 5. So whenever we divide 17 with 6, we get the value of q as equal to 2 and r is equal to 5. Other than this value, we cannot find. Right? So the unique word is, that is why use here. So we get two another integers q and r. Yes, 2 and 5 are both integers. In all three cases, 0 and 5 are also integers, 5 and 0 are also integers. Yes. So unique integers satisfying this condition. And all this 17, we divide 17 with 6. This condition is that satisfying. One condition also is that the value of remainder is in between. That means the value of remainder is greater than or equal to 0 and it must be less than of b. Let us check for the three examples. For first example, the value of remainder is 5 and it is less than b. What is b? b is 6. Right? So this number 6 is b and this is remainder 5. So 5 is less than 6. That is why remainder is less than b. For the second sum also, the value of remainder is 5 and b is 12. Again, 5 is less than 12. Third, the remainder is 0 and b is 4. Again, 0 is less than 4. So if you take another examples, and you can also check by yourself that this condition must be satisfied at that stage. Okay. So now, where to use this Euclid's division lemma? This Euclid's division lemma we will use to compute the HCF, the highest common factor of two positive integers. Right? This Euclid's division lemma we will use to find the HCF. One more concept we will study, that is called the Euclid's division algorithm. Okay? Okay. So let us understand Euclid's division lemma to find out the HCF. Let's take an example. Find the HCF of 4052 and 12576. We cannot find the HCF by the method that we have already used. Yes, we can find out the HCF of two numbers by the method that we have already studied. But whenever there are this kind of larger numbers, that method will be lengthy. So to find out the HCF of this kind of number, we can use the Euclid's division lemma. Let us understand step by step how to use. So by using the Euclid's division lemma, one condition we have to consider is that out of the two number, we have to select the greater number. So out of these two number, greater number is this. We have to divide this greater number with the smaller number. In every case, whenever we find the HCF, we have to divide the greater number with the smaller number. Yes, that is a different thing, that whenever we represent any number by the division of two number, at that time these two number, greater or smaller number, may be interchanged. But whenever we calculating the HCF, we have to take smaller number first and then divide it to the, we have to take greater number and then divide it to the smaller number. Right? So according to the Euclid's division lemma, 12,576, we can write down it as, when we divide this 4052, we will get the quotient as a 3 and 420 as a remainder. So we can say that 4052 goes 3 times and give the remainder 420. Now what? We have to use this lemma for the second step only. But which two number we have to consider? Like for the first step, we take it as a A, and for the second step, we take it as a B. Now which number we have to take as a A and B? For which two number we have to apply the division lemma? For that we have to take this number 4052, that is the B for the first step. Now it will become the A for the second step, and whatever we get as a remainder will be the B for the second step. Or in another word, for the second step, first number we have to take as an divisor number for the first step, and for the second number we have to choose remainder as a second number. So now 4052 and 420 we have selected. Again we have to divide 4052 with 420. So whenever we divide 4052 with 420, we get 9 as a quotient and 272 as a remainder. So we can say that 422 goes 9 times and give the remainder 272. So this second step also we use the Euclid's division lemma. Now is the process completed? No. Still the process is not completed. Again we have to divide the two numbers. But which two number we have to consider? Now we know that this 420 we have to consider as a first number, and this remainder we have to consider as a second number. So whenever we divide 420 with 272, what will we get? 420 is equals to 272 into 1 plus 148, because 272 goes only one time and give the 148 as a remainder. Again we have to apply this condition, Euclid's division lemma. This will be the first number, this will be the second number. When we divide 272 with 148, it will goes one time and give the remainder 124. Again we have to use this. This will be the first, this will be the second number. By dividing this, it will goes one time and give the 24 as a remainder. Now again take this 124 and 24. We divide 124 with 24, it will goes 5 times and give 4 as a remainder. Now again take this 24 and 4, divide this 24 and 4, we get the remainder 6. We get the 6 as a quotient and remainder is equals to 0. So now you can notice that whenever we do the next step, we have to divide this 4 with 0, and the division with 0 is not possible. So our process is now stop here. What we have to find out? We have to find out the HCF. So what will be the HCF? At this step, whenever we get the remainder is equals to 0, at this step, whatever is the divisor or whatever is the B, that will be the value of the HCF. So we can write down that HCF of this two number is equals to 4. Or in another word, whenever the remainder becomes 0, the previous step, the remainder in the previous step will also be the HCF of this two number. Right? So what we do, we repeatedly use the Euclid's division lemma. And whenever we repeatedly use the Euclid's division lemma, it is called as an Euclid's division algorithm. So this is simply Euclid's division lemma and Euclid's division algorithm. So in this way, by using Euclid's division lemma repeatedly, we can find out the HCF of any two given positive integers. Okay? And why this in LCM, why this HCF we get here is 4 will be possible for these two number? It is because that why this process work, because the HCF of 24 and 4 is 4, the HCF of 124 and 24 is also 4, 148 and 24 HCF is also 4. In the same way, for these two number also HCF is 4, for these two number HCF is 4, for these two number HCF is 4, and for these two number HCF is 4. That is why this process works. Okay, so this is all about this lecture. Okay, thank you.